Greetings and good day. So, welcome back to this lecture series on pulse width modulation for power electronic converters. So, in the first 5 lectures, we have been looking at various power electronic converters. We looked at DC to DC converters, voltage source converter and current source inverter and multi-level converters. And for the last couple of lectures, we have been looking at various applications of voltage source converters. This is just an overview of various applications of voltage source converters before we get on to this issue of pulse width modulation. So, as part of this overview of on these applications of voltage source converters, today is going to be the third lecture in this and the third and the final lecture in this topic. And we initially focused on the motor drives essentially in the first part, first lecture, and in the second lecture we focused on power factor correction. We looked at unity power factor rectifiers. How can you rectify, how can you have AC to DC conversion drawing near sinusoidal currents from the mains at a high power factor? That was the question we looked at. And what we are supposed to look at is today is how do you compensate for harmonic currents that are drawn. This harmonic current compensation is what we are planning to look at. So, we will be anyway quickly reviewing what done in the last couple of lectures now. As we saw, all these shows different voltage source converters. I mean, firstly we are starting with the DC to DC buck converter, and next what we have is the DC to 3 phase AC voltage source inverter, and then what we have is once again the DC to 3 phase AC multi-level inverter or the 3-level voltage source inverter, and all these have been depicted in terms of generic switches. Here you have a single pole double throw switch in a buck converter, and here also you have single pole double throw switches in a voltage source inverter VSI. So, here you have 3 single pole double throw switches for each for every phase. Now, in a multi-level converter you have 3 single pole triple throw switches. So, 1 single pole triple throw switch for each phase now. So, this is what this is what we know already. So, what we do is we realize certain average voltage. If you need certain average voltage with a 2 pole, with a 2 level inverter, we apply 0.5 VDC for certain amount of time and minus 0.5 VDC for the remaining amount of time within a switching interval. So, that the average voltage over the switching interval is equal to what is the desired value. Similarly, if you are using a 3 level inverter, you have different levels available. So, for a positive average voltage you can use you can apply 0.5 VDC for certain amount of time and 0 for the remaining amount of time as appropriate, so that you get your average voltage equal to what you want. Similarly, if your average voltage is negative, then you can apply you can realize it by time averaging of 0 and minus 0.5 VDC. So, you can realize any average voltage, any value of average voltage, that is anywhere between plus 0.5 VDC and minus 0.5 VDC. So, what we do is over a line cycle, over a fundamental cycle, the average pole voltage is modulated in certain fashion, which is usually the sinusoidal fashion. So, this is a 2 level voltage source inverter, and in every switching interval you produce certain VRO average, that is average pole voltage. R is the midpoint of this leg called the pole, and O is the midpoint of the DC bus center. VRO is the potential at R measured with respect to O, and VRO average is the average value of VRO over a switching interval. Now, let us say this is let us say this is VRO average. Now, VRO average, what we do is we modulate it in a sinusoidal fashion. Similarly, even if you have a 3 level converter, on the AC side, if you what you need is sinusoidal voltages essentially. So, one way to do this, the average pole voltage can be modulated in a sinusoidal fashion as shown here now. So, what we can do is all the sinusoids are variable, that is the amplitude of the sinusoid, as we observed the other day, can be anywhere. It can be less than or equal to VDC by 2, because the highest average voltage can be either plus VDC by 2 or minus VDC by 2. So, you can have an amplitude anywhere up to VDC by 2 with such kind of sinusoidal modulation. That is when the average voltage is being varied, average pole voltage is being varied in a sinusoidal fashion, right. So, the amplitude can be controlled and this frequency can also be controlled. You can make a sinusoid, you can realize a sinusoid which is of a shorter time period like here, or you can realize a sinusoid of a longer time period as shown here. Both these kinds of all these are possible now. So, you can vary the frequency and you can vary the amplitude, and because now, so what you have is your inverter essentially becomes a source, an AC source of variable voltage and variable frequency, and this is what you need in a motor drive. In the motor drive, you can just vary the voltage even at a fixed frequency, and certain degree of speed control could be achieved as we saw in the previous lectures, but the range of the speed control is very limited, and also this is useful only in certain applications such as pump or pump drives, compressor drives, etc. In a large fraction of motor drives, what you would need is you need a control of voltage over a larger area, I mean over a wider range of speed, and practically over the entire torque speed range. If this is your full rated torque, you basically want your control over the entire range, that is any value of torque all the way from 0 to rated torque and any value of speed all the way from 0 to full speed, that is what you want now. So, you should be able to control this at any operating point now. So, if you apply a variable voltage, variable frequency AC, you can actually shift the torque speed characteristic of the induction motor as we observed the other day. Change in frequency changes the synchronous speed. So, the synchronous speed is Ns, now let us say Ns1, Ns2, these are all proportional to the stator frequency, and if you maintain the stator voltage to be proportional to the stator frequency, the flux is more or less is maintained constant. So, you have the same magnetic field intensity and you can produce the same amount of torque. So, the peak torque does not reduce considerably when you do that. Now, this is the idea of constant V by F induction motor drive now. So, you can you operate this drive over an entire range of speed starting from 0 to full speed and torque 0 to full torque now. So, this is one of the important applications, and this is an application which we will be often using in our own course while we are dealing with pulse width modulation now. And this is essentially open loop control. You can have closed loop control as I already mentioned before, and they are dealt with in other courses under this NPTEL on motor drives, right. So, now you have these various other applications that the ubiquitous uninterruptible power supply, you find them almost everywhere. So, as we have already said, it is a battery bank and it inverts and things like that, and we also had a look at our detailed look at active rectifiers or front end converters in the last lecture. Basically, these are sinusoidal rectifiers, rectifiers which draw sinusoidal currents from the AC mains and at high power factor, and we also saw how to inject reactive power into the mains using a voltage source converter. And today the emphasis is going to, we will quickly review those things before we go on to harmonic current compensation. So, what we saw was why we needed an active rectifier. This is the conventional diode bridge rectifier, and as we observed before, the conventional diode bridge rectifier, if you consider a resistive load, the output of it will be a rectified sinusoidal waveform as shown here. Now, this waveform has some average value, but it has a high ripple on that. If you are talking about a power supply, an ideal power supply should have 0 voltage ripple. So, the voltage ripple must be negligible, but this is not the case here. The voltage ripple is considerable. So, what you try doing is the simplest thing that you can do is to put a capacitance here at the output as we have done here. This capacitance C at the output as we have done here. This helps maintain the voltage fairly close to whatever is its average value now. Once you connect a capacitance like this, what happens is the waveform, I mean the voltage across, it becomes something like this. That is, the capacitance holds the charge, the mains voltage can reduce, but the capacitance still holds the charge and the voltage remains considerably high, and again the next half cycle the capacitance gets charged again. So, you have something like there are charge discharge cycles once in every half cycle. Now, if your line cycle you take it as 20 millisecond, that is what it is at 50 hertz, every 10 millisecond it has one charge and discharge cycle. So, as we saw in the last class, if you look at this current, the current here is going to be 0 for most part of the cycle. Why? Because the capacitance voltage is greater than the mains voltage for most part of the cycle, and only for a short portion of the cycle, only a small portion of the cycle, closer to the peak voltage of this mains voltage, closer to the peak here, if I call this as Vg, closer to the peak of this Vg, you have a situation where the capacitor voltage is less than, or is not more than the mains voltage, and therefore, current flows only during that region, and that was the reason we saw yesterday that you just have such kind of pulses observed here. This duration is a very short duration during which the diodes conduct. Only during these intervals, the diodes are forward biased, and during these intervals the capacitance is charged. The rest of the interval, the capacitance is supplying the power, whatever current, whatever power is required by the load is being actually supplied by the capacitor. It comes out of the stored energy, and the capacitor gets recharged during this small intervals like this. Now, this is all right if you look at the DC side of this. It might, if you have designed your capacitance properly, sized it properly, and if your ripple is within acceptable limits, this is all right as a DC power supply for many applications. But it has a problem when you view it from the AC side. In the AC side, it draws non-sinusoidal currents. Now, that is something that we do not want, because we were talking of harmonic pollution yesterday, and it draws at a very poor power factor. That is again something that the utilities do not want now. So, we want this to be sinusoidal, and we want this to be also be drawn, the sinusoidal current also to be drawn at a fairly high power factor. These are the two things that we want now. You can see that the same story is valid for a 3-phase AC to DC also, except that here a particular diode, let us say this R plus I may call it, and R minus I may call it. So, the current, there is IR, there will be some current flowing here when R plus or R minus is conducting. So, these will conduct whenever, let us say, VRY or VBR are close to their positive peaks or negative peaks. When VRY goes close to its positive peak, there will be some conduction. Similarly, when VRY, the line voltage VRY is close to its negative peak, you will again have some conduction. The same thing about VBR being positive and negative. So, you will find instead of one current pulse, you will find actually kind of 2 current pulses in every half cycle in this kind of diode bridge rectifier. Still the waveform is highly non-sinusoidal, very far away from what a sinusoid is, and the power factor is very poor, and these are things that we really do not want, and that was the reason why we thought we would go in for an active PWM rectifier. And this active PWM rectifier, as we know, that involves active switching devices, and it tries to draw power from the mains at a high power factor, and it tries to draw near sinusoidal current, sinusoid with very little amount of ripple on top of it, such kind of a current from the mains. Now, we have looked at the question as how can we realize such an active PWM rectifier using transistors and to function as such a rectifier, I mean which draws near sinusoidal currents from the mains at a high power factor. So, we first looked at the question of power factor. So, if you want to control this power factor, what do? You have a fixed mains on this side, and let us say you have a series inductance, you connect a series inductance. Now, why? An inductor is not a bad idea in any way there, because you want to smoothen the current drawn from the mains, and the inductor has this property of smoothing the current, and therefore, you connect, let us say, an inductor in series with the mains. Now, what do? You apply certain voltage here. What is some controllable voltage you apply here. This voltage will control the power flow through the inductor, or it will control both the amplitude and the power factor of the current that you are talking about, of the current that you draw from the mains now. So, let us say you want unity power factor, that is what we have been, we want. So, this is the grid voltage. Let us say we want to draw a current I which is in phase with the grid voltage. So, it is like this. So, this is 1, this is 2. Now, because of the inductance, there is going to be a drop across because the current flowing through the inductor, there is going to be the reactive drop of the inductor, and that is this item 3 that you have. So, this is the drop across the inductor, and this drop needs to be subtracted from the mains voltage. This needs to be subtracted from the mains voltage, and that is the 4th item here. So, when you have done all this, you get what you need. This is V inverter. So, this is the controllable voltage you need to apply. If you apply an voltage of so much amplitude and at such a phase angle, let me call this delta behind Vg, and of the same frequency as Vg, then you can control I as desired. The amplitude and phase of I can be controlled now. Well, you can say that if I wants to be higher, then we found that j omega Li will be longer and your V inverter will be different. I can be of any other power factor too. For example, let me just illustrate a situation that I has some slightly leading power factor. You want to draw I at some slightly leading power factor. In such a scenario, what simply happens is this j omega Li is ahead and your minus j omega Li is something like this, and your V inverter is going to be a line like this. This is going to be a V inverter now. This is going to be a V inverter. So, all that you need to do is you need to apply the appropriate value of V inverter to draw a current of desired amplitude and phase angle. Of course, the amplitude has to be within limits. So, you can certainly do this now by applying such a voltage source. So, the question is how can I realize such a controllable voltage source or a controlled voltage source is the question now. The answer is obvious, we have a voltage source converter precisely to do that. So, you have a voltage source converter and it has a DC bus voltage. Let us presume that the DC voltage is fixed, and that is why I said closed loop control is required. Here what you essentially have, you have an outer voltage control loop and an inner current control loop. As you are aware, the outer loops are always slower and the inner loops are faster. The outer voltage loop is it takes it makes the voltage DC bus voltage steady, and the inner current loop is much faster. So, you can presume that the voltage is steady, and what the inner loop does is controls the current, and what it basically does is it specifies the amount of V inverter that really requires to be applied now. So, if you say that DC is fixed, then you can modulate the inverter appropriately, that is you can switch the devices appropriately, so that you get the V inverter that is desired. You can get any value of voltage as we saw the other day, just even a while back, that the average pole voltage can be anywhere up to VDC by 2, and VAB is basically VAO minus VBO. So, the potential here the average voltage here it can be anywhere up to VDC. So, you can get some sinusoidal voltage of amplitude up to VDC in this scenario here. So, you can basically control the voltage source, and that is what you are planning to do. That is how you realize a single phase active rectifier now. I also mentioned that this is a boost converter yesterday, right, and the DC bus voltage has to be much higher than it has to be substantially higher than the peak line to line voltage, right. So, if you say that this is the 3 phase counterpart of that, if you say I want a 3 phase AC to DC rectifier, all that you need to do is this, where you have a single inductor here, you have to have 3 inductors here and connected to the mains RYB, and you can actually have a load connected here if you wish. If you wish, you can have a load, this is in the rectification, the load is connected on that side, or the load can also be another, it can be an inverter for example. So, that is the case when you would typically tend to call this as a front end converter, because you may have an inverter feeding a motor as the load, and in this case this is the line side converter or the front end converter, right. So, hence the terminology front end converter, that is sometimes used for this FEC, we abbreviate it as FEC now. So, let us say what is the per phase equivalent, whether it is single phase or 3 phase, 3 phase can be seen by this per phase equivalent circuit. What you essentially have is you have the grid voltage VG, let us assume it to be sinusoidal at its appropriate frequency, let us say 50 hertz, and you have this per phase inductance L. Now, what you are applying is V inverter. Now, this actually what we have in this earlier case we ignored basically when we said this, we considered only the fundamental component, whereas your inverter voltage has both the fundamental component, this is the sinusoidal component, this could be the 50 hertz component, and this could be the ripple. Ripple is the sum of all the harmonics. So, the waveform that you really have there or here, for example, this waveform is either plus VDC by 2 or minus VDC by 2. If you look at this waveform here, for example, in a single phase case, you will have typical waveforms like this. You will have something like this. This is what you will have in the positive half cycle, and in the negative half cycle you will have waveforms like this. You will have the pulses being applied here. This is not sinusoid. However, it has a sinusoidal component. It has a sinusoidal component like this, but this waveform is not a sinusoid. So, what we are trying to do is we are trying to split this waveform into its fundamental and a ripple. So, the same thing that you can see here also, the per phase voltages are really like that. So, this is the fundamental component. So, this is the remaining part which we call as ripple, right. So, this is the equivalent circuit now. So, this equivalent circuit, if based on this equivalent circuit, you might want to calculate the fundamental current, or you might want to calculate the harmonic currents or the ripple current. If you want to calculate the fundamental current, you know, this is the equivalent circuit, this is the fundamental equivalent circuit, this is valid for fundamental, because this Vg is at the fundamental frequency and this V inverter is at the fundamental frequency. The ripple voltage contains harmonics and these are all at various frequencies other than the fundamental frequency, and therefore, you know, it is essentially a short as far as fundamental is concerned, and therefore, this is the fundamental equivalent circuit. And if you are looking at the harmonic equivalent circuit, both these are not there, that is Vg as well as V inverter, these are 50 hertz components. So, in the harmonic equivalent circuit they do not appear. So, what all that you have is a specific harmonic component, let us say Vn, which is the nth order harmonic. By nth order we mean its frequency is n times the fundamental frequency, and that is flowing through this inductor current L. So, the nth order harmonic voltage is going to cause an nth order harmonic current, and this current is limited only by the inductance L. Now, what is the reactance of it? As we mentioned the other day, I n will be V n times V n upon n omega L. So, n omega L is the, where omega is the fundamental angular frequency, n is the harmonic order, n omega L is the reactance seen by the harmonic voltage V n, right. So, the higher order harmonics have a greater value of n, or the harmonics in general have a greater value of n is equal to 1 for the fundamental component. So, the harmonic voltages in general see a higher value of reactance, and therefore, the harmonic currents are quite low. And you know, if when you ensure that your harmonics are at very high frequencies, say of the order of kilohertz, if you switch the inverter at frequencies of kilohertz, your harmonics are going to be of the order of kilohertz. So, you know, the ratio of the harmonic, the harmonic order is likely to be basically several tens or sometimes even 100 or so. So, the harmonic currents are very small. Why? Because the reactance seen by the harmonic voltages are very high, and that is how you achieve near sinusoidal currents. This is what we looked at. So, you can draw at unity power factor, and you can also draw near sinusoidal currents. If you want the power to flow in the opposite direction, it is possible now. This is what you do in a distributed generation. Let us say power is available from a photovoltaic cell or so, you want to pump that power into the mains. This is something that you do typically. So, then you can also control the reactive power flow excuse me. So, the reactive power flow, you want to inject reactive power flow many times. You may have other loads which are drawing reactive power, and you want to supply reactive power through a voltage source converter. So, what do you do? So, you supply, you control the current such that the current leads the voltage by 90 degrees. So, if you do that, this is the V inverter voltage, the inverter terminal voltage that is required. If you apply a inverter terminal voltage as indicated here, you will be able to control the amplitude of the current and make sure that the phase of the current is 90 degrees ahead of the grid voltage. So, from these two observations you can see that one is for active power flow, because there is some phase difference between Vg and V inverter, and now it flows from whichever one is leading to the whichever one which is lagging, that is here in this case from grid to the inverter now, right. So, here previously it was the other way also, in one case it is from the grid to the inverter, here it is from the inverter to the grid. So, in the next case where there is reactive power flow, the reactive power flow flows from something that has a higher amplitude to the other one which has a lower amplitude. So, it is the idea is very similar to the transmission line problem we looked at, right. There is some sending end voltage and there is some receiving end voltage, and this is the reactance X. So, we know how power here is controlled through the sending end voltage and receiving end voltage. So, the power flow is proportional to Vs Vr and sine of delta, which is the angle between the two voltages divided by X, and that is how you basically essentially control this power here. So, the situation here is very similar to that, and whatever you have studied in transmission can be extended. The power flow through transmission lines can easily be extended here now. So, these are the various applications based on power factor control. The first application we saw was motor drive, And the second application what we can say is something quite related to that is also is UPS, and the major set of application is these applications based on power factor control. So, you are able to have active rectifier, you are able to rectify, convert AC into DC, drawing sinusoidal currents from the mains at high power factor, and you are able to inject reactive power into the mains, or what is called a static compensator or StatCom, using a voltage source converter. So, you are able to supply reactive power to the mains, and there is also this distributed generation. Now, if you have something like a photovoltaic cell, you can pump that power back to the mains, I mean you can pump it into the mains through a power converter. And we have to look at now this question of harmonic compensation, why and how. Any load, what we had a quick look at what was the nonlinear load and what is the linear load. So, linear system, to restate what we did was they obey superposition, that is in the time domain. So, if you apply any signal u of t, it provides an output y of t. If u of t is scaled, y of t will also be scaled, and similarly that is about, and if for an input u1 plus u2, the corresponding output will be y1 and y2. If u1 results in an output y1, u2 results in an output y2, u1 plus u2 results in an output y1 plus y2. Those are the properties of linear systems. If you view that in the frequency domain using sinusoidal excitations, for a sinusoidal excitation, a linear system will result in a sinusoidal, will produce a sinusoidal output of the same frequency. So, that is the characteristic of that. So, if it is a linear load, you apply sinusoidal voltage onto that, it draws sinusoidal current. If it is a non-linear load, it will apply non-sinusoidal current here. If you just simply take a filament lamp for example, it is a linear load. Why? You apply linear voltage, it draws, I mean sinusoidal voltage, it draws sinusoidal current from that. The same is not true about a diode bridge rectifier, the same is not true about, let us say, a computer. So, this is what we saw as an example of a non-linear load, which we discussed ahead. A rectifier, the current that it draws here is not sinusoidal current. So, simply a diode bridge rectifier with capacitive filter is a very good example of non-linear load. Non-sinusoidal currents are drawn from the mains. So, what if non-sinusoidal currents are being drawn here? So, now let us say this is the voltage mains that we see. We can look at this mains voltage, the model that you can use is an ideal voltage source in series with certain amount of line inductance. Now, what you do is when you use a non-linear load, the non-linear load draws not only some fundamental current, but it also draws certain ripple current. I am indicating the fundamental current by I1 and I am indicating the ripple current by I ripple. So, what happens is this I ripple flows through this. So, that is, it consists of several harmonics. So, when harmonic currents flow through the inductor, the voltage across the inductor, there will be corresponding harmonic voltages across the inductor now. So, across this inductor you have some ripple voltage, harmonic voltages across this. So, it is not just a sinusoidal voltage, it is there are some harmonics also there. So, if you look at the mains voltage between these two terminals, this voltage is no longer sinusoidal. So, this non-sinusoidal current drawn results in non-sinusoidal voltage drop across the inductance line. This is the line inductance, and because of this the mains voltage gets distorted. It is because we have connected a non-linear load, other loads connected in parallel will also see a distorted waveform. So, that is why we use the term harmonic pollution. What we basically mean is the distortion of the mains voltage due to connection of non-linear loads. If you connect non-linear loads to the main, they tend to draw non-sinusoidal currents. These non-sinusoidal currents have a drop across the line inductor, which is non-sinusoidal in nature now. Therefore, the mains voltage itself becomes non-sinusoidal. So, this distortion of the mains voltage due to non-linear loads is what we call as harmonic pollution. Now, so let us say we want to avoid this harmonic pollution. How do we avoid this harmonic pollution? As we indicated here, there is a current flowing here. It consists of a fundamental component, it also draws a ripple component now. This is because the ripple is the sum of all harmonics, this ripple is sum of all several harmonics. Okay. Now, why is the current so? Because that is the nature of a non-linear load. So, it draws. So, if the non-linear load has to function, it needs to draw such kind of current now, but your problem is from the mains you do not want to supply a non-linear current. You want only the fundamental current to flow from the mains. As long as fundamental current flows from the mains, there is no problem. Only when harmonic currents flow from the mains, there is some issue. So, what do? You try to see whether you can have another current source which can supply this I ripple. If you can have a current source like this, now you can certainly handle this problem. You can make sure that the entire ripple current or all the harmonic currents flow from this and only the fundamental current flows from this. Is it possible? Well, it may not be for all the harmonics, at least many of the significant harmonics and lower order harmonics you can realize this. The question is, how do you realize such a current source? The answer is, well, we can use a voltage source converter to behave as such a current source now. So, what you do is, you have the same situation where you just want to draw this fundamental current from the mains and you have a nonlinear load which has the fundamental plus some ripple. I am calling it as some I tilde, let us say here, or I can also call it as I ripple as I had indicated before. So, now what I want to do is, I want to supply this entire I tilde from here. What I am trying to do is, I have a voltage source converter. I presume that the DC bus is charged to an appropriate value of voltage, right. This once again assumes closed loop control. In the outer loop, you are controlling the voltage, and the inner loop you are controlling the current, all right. Okay. So, it is possible for you to apply certain voltage at the terminals such that the effective current is what you want. The effective current is what this requires a closed loop operation. Again, the entire control is not part of this course. We are only having an overview of the application. We are trying to see the basic principle of operation as to how of active power filters, how a voltage source converter can be used for harmonic current compensation. The details of such control methods are available on other NPTEL courses. Do not want the harmonic currents to flow from the mains. So, you have provided like an alternative source. That alternative source is this voltage source converter. So, now this voltage source converter is acting like a current source which injects this ripple into the ripple current that is needed by the nonlinear load, and the rest of the current, the fundamental current comes from the mains, and this is your I tilde, and so I 1 plus I tilde flows through that. You may not be able to compensate for the entire amount of harmonics, but as I mentioned a little earlier, most of the significant harmonics can be probably cleaned up and you can produce a substantial improvement doing this now. So, what is the benefit of doing this now? As I said, you are drawing only the mains current from the the only sinusoidal current from the mains, and therefore, you are not going to result in some kind of a harmonic pollution which we talked about earlier. So, the line inductance will only see a drop due to fundamental current, and therefore, this mains voltage V g here is going to be sinusoidal. It will not be non-sinusoidal as seen by the other loads now. So, this way you are able to prevent harmonic pollution. So, this is shunt compensation, you are injecting something in shunt. So, I have now shown only a single phase case here. It is also possible to do it for a 3 phase case. So, what you are going to have here is basically a 3 phase converter with a DC bus and currents being injected here. So, these will be ripple currents, but they will be 3 phase currents, maybe 5th and 7th harmonics, maybe 5th, 7th, 11th, 13th harmonics and whatever. Now, let us say you want to compensate up to 13th harmonic, 5, 7, 11 and 13. In India, the supply frequency is 50 hertz and the 13th harmonic is 650 hertz now. You want to compensate up to 650 hertz, you need the converter to switch at a frequency much higher than 650 hertz. So, we can roughly say probably 10 times that of the highest frequency that we are interested in. So, 650 times 10 6500 or 6.5 kilohertz is what you want. So, you need switching, you need the converter to switch at a frequency in the near about of 6.5 kilohertz to be able to effectively clean up to 650 hertz harmonic kind of things now. So, the currents injected here, for example, could be 5th, 7th, 11th and 13th harmonic. So, these harmonic currents will no longer flow from the mains to the nonlinear load. Instead, these will flow from the this power electronic converter, which is called as a shunt active filter, to the nonlinear load now. So, you can have it either for a single phase or you can look at the same thing for a 3 phase situation now. So, this is shunt compensation now. So, you can also look at series compensation like what we are saying. Before that, let us take a quick look at the kind of average pole voltages that we will have. See, this was the average pole voltage. You can see that this is a sine wave. You can see that this is a sine wave. This would be the nature of average pole voltage when you in a drive application, because a motor drive requires sinusoidal voltages to be applied, and you can expect such sinusoidal waveforms in the other applications such as active PWM rectifier or such as StatCom, because what is essentially getting injected into the mains or so or drawn from the mains are sinusoidal currents now. In an active filter, what you are trying to inject is harmonic currents, some set of harmonic currents that you are trying to inject. So, the modulating signal or the way the average pole voltage waveform varies will not be sinusoidal now, it will be a combination of several harmonics. Just some indication of how possibly it could be is given here, right. So, just to make it clear that it is not sinusoidal here and it is sum of several harmonics here. So, we go on to the series compensation now. So, what do you mean by series compensation, or before that why do you need series compensation? Now, let us say you have your mains, and mains can be modeled as you said before by means of an voltage source and a series line inductance now, and we have this terminal voltage Vg. This is what is available. If you have a load, this is where you want to connect the load now. Now, let us say this mains voltage is not of acceptable quality, the quality is unacceptable. What do we mean by unacceptable quality? Maybe there could be a voltage sag, that is you may have a sinusoidal voltage there, but it may not be the voltage that is expected. If you expect 230 volts, it could be just 190 volts or 200 volts or something like that. This sag could stay on for a short while or a longer while or whatever. So, this is a voltage sag. Now, instead of being 230 volts, it could be 270 volts and 280 volts either. So, this is again unacceptable, this is not acceptable. Okay. So, you do not want it to be too lower than what is the expected value, again you do not want it to be much higher than what is the expected value now. These are unexpected conditions now. Another thing that can happen to you is the mains voltage can be distorted. Why it is distorted? Maybe there are several nonlinear loads connected in parallel, you may not have connected, others might have connected. So, there are other loads already connected like we said, and they may be drawing harmonic currents from the mains, and that has been resulting in harmonic pollution, and therefore, your Vg could be distorted. And the other thing is, it is usually it is a 3 phase supply, and the 3 phase supplies could be unbalanced. That is because of some differences in the lines are mostly due to loading. The load need not be balanced, and therefore, the 3 phase voltage is available need not be balanced now. So, you can also you will also the situation of the voltage being unbalanced. So, these are all certain issues that make the voltage quality unacceptable now. So, you want to have an acceptable quality waveform here. So, what do you do? What you can simply do is, this is your Vg, this is your mains voltage that is available, and that is not of acceptable quality. You try injecting in series with it some other waveform, which will bring your mains voltage to some acceptable quantity. Now, let us say you are suffering from a voltage sag, the problem is a voltage sag. So, what do? You try to inject certain voltage which is in phase with that. So, the two get added up, and therefore, the voltage that you see at VGM is close to what you expect, something like 230 volts. Now, let me say you have a voltage swell on the other hand. So, what do? In series with it you inject a voltage which is kind of out of phase, and therefore, your VGM will be less than Vg, the amplitude at VGM will be less than Vg, and you can get what you want at 230 volts or so. So, voltage sag or voltage swell can really be handled like that. Then what do you want to do with distortion? Let us say you have some sinusoid plus harmonics here. What you try doing is you inject those harmonics in phase opposition. You inject those harmonics here in phase opposition. So, you may not have that kind of distortion at this VGM, what is indicated as VGM. So, VGM is of acceptable quality. So, how do you do all this? That is all done by applying certain voltage here. So, who produces that voltage? It is a voltage source converter. Once again, you have a voltage source converter which is charged to certain voltage VDC. So, we presume that it is charged, and by switching the converter appropriately, the various switches modulating the switches appropriately, you can produce the required voltage, and therefore, you can go in for what is called as a series compensation. Of course, as in previous case, this requires that this VDC be maintained. So, what you will once again have is you will have an outer loop where VDC is being maintained, and this is what is called as series compensation. Now, you can look at the series compensation also for 3 phase kind of situations. So, in 3 phase, as I mentioned, there could be voltage unbalance also. So, you can use a 3 phase converter. This is only a single phase converter having 2 legs. A 3 phase converter will have 3 legs now, and then output you have a 3 phase transformer, and you can inject 3 phase voltage in series with the available mains voltage. So, the voltage that is being injected in series will add up to the mains voltage and to make the resultant voltage so in a waveform of acceptable quality. So, the voltage amplitudes will be okay. I mean if there is any unbalance, those unbalance would be set right, and if there are any distortions, the distortions could also be reasonably set right. So, you can produce 3 phase voltage waveforms of acceptable quality by following a similar approach now. So, you can also have combinations of shunt and series, and there are many things like that. As I mentioned a little earlier, active power filtering is a subject in itself, and you can certainly find information about this in certain other courses related to power electronics on NPTEL, right. Okay. So, now let us just complete and take a quick overlook at whatever we have been doing for all these days now. This is probably the third lecture when we have been covering the applications of voltage source converters. So, one of these points that we want to make is about AC motor drive. We kind of we looked at it as a one of the simplest problems and the earliest possible application. So, in an AC motor drive, you have a voltage source inverter and the DC side power supply is taken as fairly fixed. It is taken as fairly fixed, and on the AC side you want a variable amplitude and variable frequency AC. So, you are able to generate that variable amplitude and variable frequency AC, and you are able to control the speed of operation of a motor now. So, in case of an uninterruptible power supply also, you have a voltage source inverter which is feeding some AC load. Well, that AC load could be of any power factor or whatever that you might think of. So, it may have a range of power factor. So, in this situation, in the case of an uninterruptible power supply, what you need is the DC voltage will be inverted into 50 hertz or 60 hertz, whatever the standard may be in that country. So, it will be a 50 hertz output voltage is all that you will produce. So, the output frequency will not change, whereas in an AC motor drive, the output frequency will vary over a considerable range. Maybe it can vary over from 1 hertz to 50 hertz or 2 hertz to 50 hertz or up to 60 hertz or whatever, it can vary now. So, here on the other hand, in an uninterruptible power supply, the output frequency does not change now. Also, the output amplitude might not change. The output amplitude has to be whatever is the desired value. So, its range of operation in terms of modulation index and frequency is pretty much limited in the case of an inverter, which is part of an uninterruptible power supply. Now, you also use voltage source converters in active rectifiers or front end converters. We just saw this because when you want rectification, that is when AC is available and what you expect is DC, you need rectification. As we saw a little earlier, rectification, if you can just use diode bridge rectifiers to do this, but a diode bridge rectifier cannot give you whatever voltage that you desire. It can give you only a fixed voltage, and this fixed voltage is it is related to the peak line to line voltage in the mains, and there will be also some amount of regulation. This voltage may not be really fixed that way, you can't really control that voltage. So, if you want to control that voltage, you go into other kinds of rectifiers which are not you go in for thyristor rectifiers. That was the next stage. With a thyristor rectifier, you can control the DC output voltage, but still a thyristor rectifier also draws non-sinusoidal currents. So, you draw non-sinusoidal currents and the waveforms are distorted and the power factor is very poor. These are the problems that you have. That was the reason why we went for active rectifiers or front end converters. So, if you quickly look at what we are able to do is a PWM converter with a fixed DC bus voltage is able to produce an output voltage of desired amplitude and desired phase. So, the amplitude and phase are such that there is a line inductor and it is able to control the power that flows through the line inductor. So, in active rectifiers, what do you have? You essentially have a PWM converter with line inductors in series now. So, one side of the line inductor you have the mains voltage, the other side of the line inductor you have the PWM converter. So, this PWM converter applies a voltage of appropriate phase and amplitude such that the current that flows through the lines, that is through the inductor, is of the desired amplitude and desired phase, or power is drawn at the desired power factor. So, you are able to control the power factor and you are able to draw near sinusoidal current through this. As we saw, the fundamental current is being controlled and the harmonic voltages are there, but they get fairly filtered out by the line inductors, and so the ripple current, the harmonic currents are much lower in amplitude than the harmonic voltages as we saw some time back, and the currents are near sinusoidal, apart from the fact that the power is being drawn at a high power factor now. So, in active rectifier what we saw was the power factor is being controlled to close to unity. Rather you can make sure that the power factor is not unity, but it is 90 degrees. The current is leading the voltage by 90 degrees. If you do this, you go into what is called as reactive current injection. Now, it is what you would call as reactive current injection. So, this in this case of you may have other loads which are drawing reactive power. So, what you try to do now is you supply reactive power through voltage source converter. So, you know this or sometimes it is also called static compensator. I mean, now we are particularly talking of reactive current compensation. So, you may have other loads which draw a lot of reactive power. So, you have such a compensator available, then you have much less I mean this is supplying the necessary amount of reactive power. So, your overall power factor will be much better now. And the most recent thing that we saw just a while back was harmonic current compensation, or what is called as active power filtering. This is active filtering of power. So, you may have harmonics being drawn there. What you are trying to do is, if harmonic currents are required by certain load, you supply those harmonic currents. And similarly, if harmonic voltages are required, let us say the mains voltage available already is distorted. So, what you try doing is, you inject in series with it certain harmonic voltages which are out of phase with the harmonic voltages that are part of the mains voltage. So, the resultant will produce a waveform which is reasonably independent of all these kinds of distortion. So, these are the various applications that we saw, and once again I would emphasize that it is just an overview of these various applications. We have only seen the basic operating principles, and you should look for the details in certain other courses that may be available for you, that are available. Now, let us just sum up a few things. So, what is it that we saw? In all these various situations, what we had was a box, I mean a power converter, and this power converter has DC on one side. So, it is fed from some DC power supply or whatever it may be, or maybe the load is on this side or the source is on that side, we will come to that a little later, and it has AC on the other. So, let us say it is a 3-phase AC. What does this this box comprise of? It has several switches. So, this is a power converter. Now, this produces 3-phase AC on the other, and what I would like to stress is, this is really a bidirectional power converter. So, power can flow in either directions. First, if I say that the power is flowing in this direction, let us say the current is flowing in this direction, like here. So, that means power is flowing from the DC side to the AC side. If this is reverted, let me just change. Now, let us say in this the DC current is flowing in the other direction. What do you mean? Power is flowing from the AC side to the DC side. In the first case, what is shown with the red ink, power is flowing from DC to AC side. There, if you look at the fundamental voltages and you look at the fundamental currents, they will be more or less in phase, or the phase angle will be within 90 degrees. If you look at the second case, that is the green ink one, you have on the AC side 3-phase voltages. The 3-phase voltages have their fundamental and components. The 3-phase currents have their fundamental components. If you look at the fundamental voltage and fundamental current on the AC side, they may have a power factor, I mean they may have a phase difference close to 180 degrees, between something like 90 degree to 270 degree. So, let us say around 180 degrees. So, that is a situation where power is really flowing from one side to the other side now. So, this converter could really be anything. It can be a 2-level converter, or it can also be a 3-level converter. So, or it can be any other thing replaced now. So, these are certain things which are applicable for any kind of converter which has DC on one side and the AC on the other side now. What will our focus be in subsequent lectures? You can produce, see now all these applications require you to produce certain DC voltage, certain AC voltage given a particular kind of DC voltage. How do you do that? You do that by doing this pulse width modulation. You have a set of switches, it may be a 2-level converter or it may be 3-level converter or whatever, but all that you have is set of switches. So, these switches have to be turned on and turned off in a particular fashion at particular instance, and that will have to result in the desired amount of fundamental voltage. So, our issue focus is going to be on this PWM. So, what does it do? It provides all the necessary gating signals, the gating signals for the devices. So, our job is to see how should you produce these gating signals, or what kind of gating signals that you produce. for a given amount of DC bus voltage, and let us say a given amount of fundamental voltage on doing this now. So, there are very standard methods of doing this, and there are also certain modern methods or relatively less known methods available now. Our idea here will be to explore the various possibilities. Let us say you have a DC bus voltage. Let us say this DC bus voltage is equal to some 600 volts. Let me say this is 600 volts. Let me say you need a fundamental voltage, and that fundamental voltage is equal to should I say 230 volts, 230 volts phase RMS. This is what you want now. So, this voltage 230 volts can be synthesized out of this through very many methods. So, one of the constraints here is about the switching frequency, how fast you can switch an inverter now. So, the switching frequency has some relationship with the power level at which you are operating. Switching frequency has some relationship with the power level at which you are operating. So far, we have been dealing with only ideal switches, but remember, switches have non-idealities. Ideal switches have no dissipation, whereas non-ideal switches have dissipation. What are those dissipations? One is conduction loss. Ideal switch has no forward drop, whereas a real switch has certain forward drop and therefore certain amount of conduction loss. And not only that, an ideal switch turns on and turns off in no time, instantaneous switching transitions, whereas real switches take a finite amount of time to turn on and turn off. And during the switching transitions, what happens? Both the voltage and current are significant. So, there is certain amount of switching energy lost. Ideally, in a switch there is no loss at all, power loss at all, because in the forward state the voltage is 0, I mean in the on state. In the off state the current is 0. So, the product VI is always 0. So, that is how you have very little loss in a switch, whereas while a switch is undergoing a switching transition, both the voltage and current could be substantial simultaneously, and this produces a certain amount of switching power loss over that interval. So, certain amount of energy gets lost every time you switch converter now. So, if you are talking of a high power converter, the switching energy lost is going to be much higher. So, the overall power is product of the energy that you lose in every cycle multiplied by frequency. So, when you talk of high power, the switching frequency is, I will call this as FSW, the switching frequency is going to be low, whereas at lower power levels it could be high now. So, the switching frequency is also related to the power levels at which you are operating. So, what I am trying to say is there are very many ways of producing the same 230 volts now and taking care of the switching frequency constraint. If you are talking of high power converter, the switching frequency can be low. Even at a low switching frequency, it is possible to produce this desired fundamental voltage in multiple ways. So, what we will be exploring in this course is how you can produce the desired fundamental voltage out of a given DC bus voltage in multiple ways, and if there are multiple ways, how can you go about evaluating the different options that are available. So, what could be the basis for evaluating various options and how you will be doing it. So, we will be doing this starting with, we will be focusing just on a 2-level converter, which is something there, and then if we understand the modulation for a 2-level converter, it should be reasonably easy for us to extend it to 3-level converter. So, these are certain things that we will be doing in this course now. And while coming to the PWM design, one thing that is of importance is also the application, because as I mentioned a little earlier to you, if you are looking at a motor drive, the modulation, the range of modulation, sometimes when you are close to the full speed of the motor, your modulation index is very high, you are producing a fundamental voltage close to the full voltage. If the motor drive is operating at a low speed, then the modulation or the AC side voltage is very low. On the other hand, if you are talking of a line side converter, a grid connected converter, the modulation range is not very different. I mean the frequency of modulation is always the line frequency, there is no variation, and again the modulation index or the range of the fundamental voltage that you produce in this is not too very different, it is within a finite range now. The same way it depends on the application now, and sometimes you may be drawing, if it is an active rectifier, this phase, I mean the mains voltage and the current are in phase. If it is a STATCOM application, the phase, I mean the current and the voltage are 90 degrees, have a phase difference of 90 degrees. All these affect the losses, particularly the switching losses, etc. I mean the losses suffered by the inverter are affected now. So, we will be dealing with certain how do you evaluate losses in pulse width modulated converters, that is something we will do, and we will also look at is it possible to design converters such that the losses can be reduced under given operating conditions? That would again be another endeavor that we will have. So, we will be doing all this now. So, henceforth our focus will move on to pulse width modulation. So, if you remember your first thing, that is, let me excuse me. So, if you go to the first slide, what we have been looking at is pulse width modulation for power electronic converters. So, we have been dealing with power electronic converters all through these days now. So, what we will move on to will be pulse width modulation henceforth. We had a look at varied kinds of power electronic converters such as DC to DC and voltage source inverter, current source inverter, 2-level converter, multi-level converter, etc. And then we looked at these various applications. So, now we will be moving on from the next lecture onwards towards this modulation, towards pulse width modulation. That is what we will be doing now. So, thanks for your interest, and we hope to continue this in the next class. We will start looking at some fundamentals of pulse width modulation in the next lecture. Thank you very much.